Hello everyone, we are teachers from the Department of Statistics at the Chinese University of Hong Kong. Welcome everyone to our video. Today I want to talk to you about confidence intervals. It is a very important tool in statistics and can be used to estimate some unknown population parameters. Everyone, look at the screen. Our content today is roughly divided into several parts. In the first part, I will explain the concept of confidence intervals and its definition. Then in the next part 1 will explain how to use the pivotal method to construct confidence intervals. We will use a quantity called pivotal quantity. In the next part, I will talk about how to use the large sample method to construct them. We are based on the method of normal approximation. In the last part, I will give you some exercises to practice what you just learned. Let's start from the first part. A confidence interval is an interval estimator that can be used to estimate population parameters. This interval estimator usually has two values. The first is the lower limit, and the second is the upper limit, usually represented by theta hat sub L and theta hat sub U. Here theta hat is the estimated parameter. If you think about it, this interval should have two characteristics. First, it should contain the target parameter theta with high probability. And second, it should be narrow. Our goal is to find an interval estimator. These very narrow intervals can be calculated, and there is a high chance that the theta will be included. Next we will define confidence intervals. We actually have two types of confidence intervals. The first is two-sided and the other is one-sided. Let's first talk about two-sided confidence intervals. Suppose we have two values, called lower confidence limit and upper confidence limit, used to estimate a certain parameter theta. If our lower limit is smaller than the parameter, then the chance of it being larger than the upper limit is equal to 1 minus a very small number alpha. For example, 0.05. This probability minus alpha is called confidence coefficient. The range defined by these two values is called two-sided confidence interval. Let's talk about one-sided confidence interval. It can also form a one-sided confidence interval. This time we will make the lower limit the probability that it is less than or equal to the parameter theta, which is also equal to 1 minus a very small alpha number. For example, 0.05. In this case, our confidence interval will extend from the lower limit to positive infinity. Similarly, we can also construct an upper one-sided confidence interval. This will make the parameter theta less than or equal to the upper limit. The probability is also a small number minus alpha, such as 0.05. In this case, the confidence interval will extend from negative infinity to the upper limit. Now that we have confidence intervals defined, let's see how to find them in different ways. The first method that will be introduced is pivotal method. The pivotal method is based on finding a pivotal quantity, which will have two characteristics. The first is that it is a function of the data and the unknown parameter theta. Theta is a unique unknown quantity, and its probability distribution does not depend on theta. For example, we can use U equals x bar minus theta over s as the pivotal quantity. where x bar is the sample mean and s is the sample standard deviation. U means that there is a known distribution. We can use the following method to find the required confidence interval. Once we have the pivotal quantity, we need to find two numbers a and b such that the probability that the pivotal quantity will be between a and b is equal to 1 alpha. Then we will use these numbers to calculate theta, and we will get an interval for theta. The probability of this interval will be 1 alpha. Let me give you an example to see how to use pivotal method to construct confidence interval. Suppose that we have a single observation y from an exponential distribution with mean theta. We want to use y to form a confidence interval for theta with confidence coefficient 0.90. Suppose we have an observation value y produced by an exponential distribution, and the mean of this exponential distribution is theta. To apply the pivotal method, we need to find a pivotal quantity that satisfies the two characteristics that I mentioned before. One possible choice is u equals y over theta. By using the transformation method, we can check that u follows an exponential density function with mean 1. Hence, u equals y over theta is a function of y and theta, and the distribution of u does not depend on theta. Thus, we can use u equals y over theta as a pivotal quantity. Next, we need to find two numbers a and b so that the probability of u between a and b is equal to 0.90. That is to say, the probability of u is less than a is equal to 0.05, and the probability of u is greater than b is equal to 0.05. By solving a and b from p equals 0.05 and p equals 0.05, we get a equals 0.051 and b equals 2.996134. It follows that p equals 0.90144. Then we can solve for theta. We also get p equals 0.90. Thus, the 90% confidence interval for theta is The pivotal method is useful for constructing confidence intervals when we have a known distribution for the data and a suitable pivotal quantity. However, in many cases, we may not have such information or the pivotal quantity may be difficult to find. In those situations, we can use another method called the large sample method, which is based on the normal approximation for large samples. The large sample method relies on the fact that for large samples, many estimators are approximately normally distributed. Then for the target parameter theta, z equals theta hat minus theta. Over sigma sub theta hat follows approximately a standard normal distribution, where theta hat is the estimated parameter, and sigma sub theta hat is the estimated standard deviation of theta hat. Consequently, Z forms a pivotal quantity, and the pivotal method can be employed to construct confidence intervals for the target parameter theta. The procedure of the large sample method is as follows. First, we calculate the point estimate theta hat and its standard error sigma sub theta hat from the data. Second, we select two values in the tails of the standard normal distribution, z sub alpha over 2 and negative z sub alpha over 2. Such that p equals 1 minus alpha. Third, we construct the confidence interval by adding and subtracting z sub alpha over. Two times sigma sub theta hat from theta hat. Let me show you some examples of how to use the large sample method in practice. The first exercise asks us to find a confidence interval, which is again the range of values we are fairly sure our true value lies in. We're looking for a 95% confidence interval for sigma squared. Here, y is normally distributed with mean 0 and an unknown variance sigma squared. The square of y divided by sigma squared follows. A chi-square distribution with 1 degree of freedom. The solution involves using the pivotal quantity. Which is the square of y divided by sigma squared. The values of a and b are found to be approximately 0.00098821 and 5.02389 respectively by checking the chi-square distribution table. This leads to the 95% confidence interval for sigma squared as the square of y divided by 5.02389 and the square of y divided by 0.00098821. The second exercise is similar to the first one, but it asks for a 95% upper confidence interval for sigma squared. The value of c is found to be approximately 0.00393321, which leads to the 95% upper confidence limit for sigma squared as the square of y divided by 0.00393321. The third exercise again follows the same pattern, but this time it asks for a 95% lower confidence interval for sigma squared. The value of d is found to be approximately 3.84146, which leads to the 95% lower confidence limit for sigma squared. as the square of y divided by 3.84146. The final exercise is about constructing a 95% confidence interval for the mean length of stay of patients in a hospital. A random sample of 500 hospital patients has a mean and standard deviation equal to 5.4 and 3.1 days, respectively. This time we want to calculate the 95% confidence interval for the mean length of stay of patients. We are going to use the large sample method this time. We need to assume that our sample mean x bar is approximately normally distributed for large samples. Then we can use z equals x bar minus mu over s over square root of n. As a pivotal quantity, where mu is the population mean that we want to estimate, s is the sample standard deviation, and n is the sample size. The point estimate for mu is x bar equals 5.4 days, and the standard error for x bar is s over square root of n equals 3.1 over square root of 500. For a 95% confidence interval, we choose z sub alpha over 2 equals z sub 0.025 equals 1.96 from the standard normal table. Then we construct the confidence interval by adding and subtracting 1.96 times 0.1386 from 5.4, which is hence, the 95% confidence interval for mu is days. This concludes my talk on examples on confidence intervals using different methods. I hope you have learned something useful from this session. Thank you for your attention and have a nice day.